So mercifully, we finished off alkane nomenclature last time, and we looked at a number of examples. The first number of examples we looked at were with respect to alkane nomenclature of linear systems. And then we moved into cycloalkane nomenclature and showed a number of examples of that. And lastly, within the realm of cycloalkane nomenclature, we did have to touch on and discuss and describe geometric isomers of cycloalkanes. And we gave some, that cis and trans business that we saw in the last lecture. We had to apply that to certain cycloalkane or di-substituted cycloalkanes. And again, we looked at a number of examples of that. So what we'll be getting into now, we're going to swoop back and just start looking at the nature of carbon-carbon single bonds, and particularly their ability to rotate around that carbon-carbon single bond. We will be getting into examples of things that are or alkanes which may not look the same, but they are the same compound. These are known as conformations of alkanes, and we'll look at conformations of linear alkanes. Basically, remember when we were talking about geometric isomers, cis and trans, we could not have one geometric isomer sort of wiggle around and become the other geometric isomer. They were separate compounds. Well, we have, at least with respect to linear alkanes, the ability to look at these two ways of viewing the same compound. So due to free rotation around these carbon-carbon single bonds, these linear alkanes can adopt different ways of expressing themselves known as conformations. They're all representations of the same compound. So for instance, here is a three-dimensional example or rendition of ethane. And we have the ability to rotate around that carbon-carbon single bond on both of these, sort of drawing that here so that it can rotate into two different conformations. Now, so if we look at this and we rotate it a little bit around, so if we look at the example on the left, rotate it a little bit around the carbon-carbon single bond which connects the two carbons, we would see that we come up with two different ways of looking at this. Notice on the structure on the left, it is known as the staggered conformation of ethane, in which this hydrogen atom sort of bisects the two hydrogen atoms on the adjacent carbon. However, if I rotate, and actually 60 degrees, we get what's called the eclipsed conformation of ethane on the other side, where these two, if we were sighting down the carbon-carbon bond, these two hydrogens would eclipse one another. So let's take a look at that. We will imagine that we are sighting down both of these carbon-carbon single bonds right down this way, and we can look at this from an end on here. And if we did that, we would see over on the left-hand side the staggered conformation. That near hydrogen is certainly bisecting those two far hydrogens. That is enigmatic, specific to the staggered conformation. Whereas on the other side, we see that the near carbon is eclipsing, the near hydrogen is eclipsing that far hydrogen, which we see in this case right here. In fact, when looking at the difference between the eclipsed and the staggered conformation, we can see that the two hydrogens on the eclipsed conformation on the right that I've shown here are closer together than any two hydrogens within the staggered conformation. Now, it's not much of a distance difference, but it certainly is there. So we can now make some stability arguments for which one is more stable than the other. we find that since these two conformations can go back and forth between each other, if we ask the question, well, which is the more stable conformation, it would be the one in which these hydrogens and their covalent bonds, as regions of electron density, are farther apart. Remember, because as these bonds and their hydrogens get closer together, those covalent bonds are made of electrons holding the negative charge. As they get closer together, like charges repel, it becomes more unstable. So what the more stable conformation would be the one in which the hydrogen atoms and their bonds are further apart. So thus, the more stable conformation would be the staggered conformation over on the left-hand side, because it minimizes electronic repulsion or electron repulsion, because the hydrogens and their bonds are a little bit further away from each other than they are on the less stable conformation, the eclipsed conformation. So because those hydrogens and bonds are closer together on the eclipsed conformation of ethane, it is considered less stable, less stable. So let's look at a larger system on our conformations of linear alkanes. Let's look at butane, our 4-carbon alkane, and specifically, let's look or cite directly down this this central carbon-carbon bond, this central carbon-carbon single bond on both of these. And we find that if we were to carry out a rotation around this central carbon-carbon single bond, we could rotate between two different conformations. These different conformations are the staggered conformation of butane over on the right-hand side. And if we do that, look at the disposition of these bulky end methyl groups. Well, one is over here on the staggered conformation, and one is way over here. This is as far apart as they can get. So if we were to rotate into the eclipsed conformation, that puts these two bulky methyl groups right on top of each other, very close to one another. And these bulky methyl groups are made up of nothing really more than electrons in those bonds. So in which case do we see these regions of electron density closer to one another? Well, that would be in the eclipsed conformation. We can see this again in another way of looking at this down below. It's just about the same sort of thing, in which we have, again, another sort of model picture of our staggered conformation over on the left-hand side, which can rotate around that central carbon-carbon bond to form over on the right our eclipsed conformation, which we see here, which could then rotate into the back into the staggered conformation. Again, let's look at the disposition of those methyl groups. If we can, on the staggered conformation as before, they're very far apart, very far apart. But on the eclipsed version, they are right on top of one another, very, very close. So looking up at the top pair, we can say, well, we can rotate in between one another, but what if we wanted to ask the question, which of the two conformations is more stable and which is less stable? Well, the more stable one would be the one that keeps those methyl groups as far away, for those end methyl groups as far away from each other as possible. And that would be the staggered conformation of butane. Much more easy to see on this one. And the less stable conformation would be the eclipsed conformation of butane. Again, much easier to see than the ethane we saw on the previous slide, because there's a huge difference now between where those methyl groups are disposed far away from one another or right on top of one another. So we had said before, in order to be able to have carbon-carbon alkane single bonded structure, to be able to freely rotate, it cannot be in a cycle. Remember when we formed an alkane cycle, a cycloalkane? Well, those carbon-carbon single bonds were restrained and constricted from free rotation. They could wiggle a little bit, as we're going to show you here, but they cannot freely rotate. So we're going to look at conformations specifically of cycloalkanes here. Cycloalkanes. Now, as we saw in the previous lecture, there are many different cycloalkanes: cyclobutane, cyclopentane, cyclohexane, cyclooctane, anything we really like. But specifically in this class, we're only going to be considering cyclohexane as an example of conformations of cycloalkanes. Because it's the most understood, it's the most well understood, the most well studied, and each cycloalkane has a different sort of conformation profile. That's why we're cutting this short and only looking at the well-studied conformations of cyclohexane, as we see right here. Now, this is a perfectly reasonable line drawing of cyclohexane, but it's in 2 dimensions. And these 2 dimensions show this just as a simple hexagon. This is an alkane, an alkane. So what was the preferred bond angle in an alkane? It was 109.5 degrees. If I draw a geometric hexagon, that bond angle is much greater, actually, than 109.5 degrees. And it is desirable for, to put a human factor to it, desirable for that cycloalkane, that cyclohexane in this case, to re-achieve 109.5 degree bond angles. And it does that by forming preferred conformations in order to reapproach that 109.5 degrees. So what we get, and we'll move to a model here to show you, and you can sort of trace, you can see trace the carbons in your mind right here in that cycloalkane. We have sort of a squiggle to it. As a matter of fact, if I draw this 3-dimensionally in a line drawing, we get what's called the chair conformation. You can trace out a chair in your mind, whether you're looking at that model of a complete bonding structure or a line structure, but it's called a chair because if you think about, say, an easy chair or a lazy boy or something, you know, this would be considered the backrest. Here is the seat, and here is the part where you'd put your feet. So that's considered a chair, if you will. But I will say that in this now squiggly conformation, the conformation of cyclohexane, that the bond angles in them have reapproached and have reapproached 109.5 degrees. So this is the way that this is why a carbocycle like cyclohexane does not lay flat. It is not planar. It actually has some 3-dimensionality to it, and that's all about reapproaching 109.5 degree bond angles. So we have our chair conformation, but in the last 2 slides we looked at, there were 2 conformations, and we were looking at differences between them. Well, the chair conformation of cyclohexane can indeed form something else, and ask yourself, what would happen if we flipped up this footrest on the chair? What would that make if we flipped that upwards? Well, we get something that looks like this. And indeed, this chair conformation can go back and forth to this new conformation. So trace out those 6 carbons on the right in your mind and see what that makes you think of. It actually looks like a boat. So if we look at that in a line drawing, it looks like a little boat. So that's indeed what this is called. It's called the boat conformation of cyclohexane. So we have the chair conformation and the boat conformation, which can interconvert. Again, looking at the boat conformation on the right here, what would happen if I took this edge up here and just tipped it back downward? The reverse of what we did before. Well, it would go back to the left and reapproach the chair conformation. One thing I will say is that whether you're in the chair conformation or the boat conformation, both of them allow for the reapproachment of 109 degree bond angle within that structure. So that's ultimately good. Never do we get a very flat, planar structure of those 6 carbons. It's either in the chair conformation or the boat conformation. So here's the question. Just as we saw in the last couple of slides, which conformation would be more stable? And remember, we had the staggered and eclipsed versions or conformations of ethane and butane, and one of them we found the eclipsed conformation on both were less stable because it brought those regions of electron density in closer proximity. Well, we're going to ask the same question about the chair and the boat conformation of cycloalkanes. And if you'll notice now, in the boat conformation over on the right of cyclohexane, we have some issues here with 2 of those hydrogens getting pretty close together. You see that right there, where we have so those 2 hydrogens on the very end are getting much closer to one another, and the closer they get, they bring their covalent bonds in closer proximity, and those covalent bonds are made of electrons, which carry the negative charge. The closer 2 negative charges get to one another, the less stable it is. So thus, the boat conformation is less stable than the chair conformation, which is more stable. The more stable structure minimizes that electron repulsion by putting those electron groups further apart than in the less stable conformation, in this case the boat conformation. Well, we're maximizing this electron repulsion, and that's not good. So even though these 2 conformations move back and forth between one another, if we had to say which one of those 2 conformations, the chair or the boat, is more stable, we'd have to say the chair conformation. And the reason being because it minimizes electron repulsion. So finally, we have arrived, if you want to look at it that way, at what we're really here for. This is a chemistry course, organic chemistry. So in chemistry, we like to undergo chemistry, undergo chemical reactions. And we're going to see that organic reactions are treated a little bit differently than standard reactions you may be used to in general chemistry. But there is always one type of reaction of hydrocarbons that, number 1, is very easy. And number 2, doesn't really fit the profile of an organic reaction. So we're going to introduce that here before we go full on into what an organic chemistry reaction really is. And this harkens back to the reactivity of alkanes or hydrocarbons in general. Alkanes, as a representative of hydrocarbons, are very non-reactive, very unreactive. Carbon-carbon single bond structure. So typically, so we don't have a lot of chemical reactions or organic reactions even that we're going to be showing you for alkanes because there's not a lot of them. However, if there was one reaction, if you were in a pinch and you needed some sort of reaction for a hydrocarbon, you can certainly burn it. So this harkens back a little bit into general chemistry of balancing combustion reactions of hydrocarbons. We can always burn it. In a combustion reaction of an alkane, which is a hydrocarbon, oxygen, O2, is always a reactant, and carbon dioxide and water are always products. And we can set this up just knowing that. Now, and ultimately it involves a balancing of an equation, a very general chemistry thing to do. So this is the bridge. We're really not talking about organic reactions yet, but it is a reaction we can carry out on an alkane. Burn it, right? So what if we had something like this? Cyclohexane burns in the air. Balance the reaction equation. Okay, well, there's some code in here. Cyclohexane, that's the hydrocarbon that we're going to be burning, burns in the air. Well, air, what's in the air? Oxygen. Well, oxygen's a reactant. And we're going to balance the equation knowing, or hopefully memorizing, that carbon dioxide and water are always products. And we would set this up in a standard way of balancing a chemical reaction. Here I've drawn cyclohexane in that two-dimensional line drawing way over on the left, and I've set it up to plus certain number of O2 molecules goes to certain number of carbon dioxide and water molecules. In order to do this, we have to, since it's a general chemistry problem, we have to convert that cyclohexane into an actual molecular formula. Well, hexane has 6 carbons, and since it's a cycle, 2 times 6 would be 12 hydrogens. Remember, 2N? So it's actually C6H12. That's how we would handle it in this case. And we would always put a 1 in front of that C6H12, and then look over on the other side. Let's balance carbon first. If we have over on the left, we have 6 carbons over here. Well, carbon dioxide is the carbon-containing component here, so we would need, since there's 1 of those per CO2 molecule, we need to put the number 6 right there. Well, we'll go back now and look at hydrogen over on the left. There's 12 hydrogens. Well, water is the hydrogen-containing component here, and it's 2 to a packet. So to achieve 12 of them, we'd put the number 6 there as well. Lastly, we need to balance oxygen. So we need to count up the number of oxygens on either side. So there is actually, 6 times 2 is 12, and 6 times 1 is 6. So there's 18 oxygen atoms on the product profile side. So how many oxygen atoms, the same number of oxygen atoms, need to be on the other side? And we find that they come 2 to a packet. We need 18 of them, so we put the number 9 there. And thus, it is a balanced combustion reaction of a hydrocarbon. Again, going back to my caveat, that is not a standard way of carrying out an organic chemistry reaction. So let's look at what is the proper way of looking at an organic chemistry reaction. So now we're going to be introduced into what organic chemical reactions actually look like. So since we're being introduced to this, it's obviously going to be different than the usual flavor of chemical reactions we've been seeing in general chemistry, which are usually governed by molecular formulas, and they happen to be balanced to adhere to the law of conservation of mass on both sides of the equation. So let's look at how these organic chemical reactions are depicted differently. So first of all, organic reactions are always functional group interconversions, meaning the molecule on one side may have one functional group on it, but by the time it gets to the other side, into the product profile, it is a different functional group. Almost always, it's a functional group interconversion. We start on one side with an alkene, maybe on the other side it goes to an alcohol. Or we start on one side as an aldehyde, and that functional group interconversion into the product profile produces, say, a carboxylic acid. It's going from one functional group to another. They're set up in the following fashion. This is just a written fashion. It's not how they're actually given, but it's to show you that we have recurring themes throughout these organic chemical reactions. So as just an example, very important, it's just an example, we might have an alkene drawn out as a reactant. Then in an organic chemical reaction, typically, not always, but typically we treat it with some sort of reagent that induces that reaction to be carried out. Most of the time, we have a set of conditions, not always, but most of the time, a set of conditions put above the arrow. Now, that could be the type of catalyst used, maybe heat was added, maybe we have other conditions, light or something like that in there. So any other conditions required to make that organic reaction go are typically written above the arrow. And then here we are with our product profile, in this case, an alcohol product. Notice an alkene to an alcohol is indeed a functional group interconversion. So how do we put these together? Typically, when depicting organic chemical reactions, we are drawing pictures. We're drawing pictures. Organic reactions are typically drawn or laid out in a pictorial fashion, whereas general chemistry reactions, as I said before, are typically just having molecular formulas on one side, molecular formulas on the other side. In organic chemistry, we draw pictures. So this way of expressing, remember we described the components here in an organic reaction. Let's give an example how that depiction would be drawn in general. This is just one possible example. You're not meant to memorize it right now or anything like that, just to see as an example how these organic chemical reactions are put together. So here, and we don't have to write out alkene, but it's just showing that, okay, there's a reagent, and you know, that sort of thing. But indeed, we've drawn a picture to depict this alkene. This is our reagent, in this case, water. Over our arrow here are our conditions, catalytic hydronium or catalytic acidic conditions. Over on the product side, here's a picture of two products that come out of this reaction. So perhaps you can see, as I've been describing, this is sort of like drawing pictures, very different than a standard general chemical reaction where we just go to molecular formulas. Now, importantly, let's look at a third idea here behind the concepts of the depiction of an organic chemical reaction. Organic reactions frequently appear to not adhere to the law of conservation of mass because we're drawing pictures, and I'll show you why in a moment. But in fact, they always do despite this. Now, regardless of this, so let's look at this. Let's look over on the reactant profile on this one. I count total on this side from my picture 1, 2, 3 carbons. That's it. There's no number in front of there. Maybe there should be, but there isn't because we're drawing pictures. 3 carbons. Now let's look over on the right-hand side. The product profile, I count 1, 2, 3, 4, 5, 6 carbons. What's going on? I see 1 oxygen here. In fact, I see 2 oxygens over there. This appears not to adhere to the law of conservation of mass. It in fact does. We overlook that because we're drawing pictures. What this means is that we have a certain number of these alkene molecules right here. Some of them react with the water reagent to form this product. Some of them react to form that product. The total number together would be the number of these molecules. It's just not depicted in an organic chemical reaction because we are drawing pictures. Yet, it always does adhere to the law of conservation of mass. That's just a little departure from the way that we've been looking at these things, these chemical reactions up till now. All right, here's our first bona fide organic chemical reaction. And it is of an alkane. Since we're looking at alkanes, these are the reactions of alkanes. Remember when I said, oh, alkanes are very non-reactive, so therefore let's burn it. That'll go in the column of a reaction of an alkane. Well, there's one more that we're going to look at, notable reaction of an alkane, and that's known as the halogenation of alkanes. Notice in this very general picture here, I have an alkane and I have my reagent here. That reagent is a halogen. Notice it's written as X2. Well, though, that X can be either chlorine or bromine, Cl2 or Br2. Now, you might think that, well, there's a couple of other halogens. There's F2 and there's I2. That is true. However, in the halogenation of an alkane, it only works predictably when we use chlorine or bromine. So just Cl2 or Br2. So that's our reagent. Notice over the arrow we have our conditions. This reaction requires either intense light or intense heat to proceed. not both of them. Notice the or. It's either intense light or intense heat. And when that happens, we have a functional group interconversion. And specifically, alkanes undergo what are called substitution type reactions. They're substitutions, meaning that between the alkane in this case and the reagent, we trade off, we substitute. The reagent says, here, I'm going to swap something with you, and I will take something of yours. That's called a substitution reaction. And what ultimately happens going from our reactant profile to our product profile? Well, if we look at this over on the reactant side, this hydrogen on the alkane is swapped out for one of the halogens. And that hydrogen, in fact, travels over to the remaining halogen and becomes a side product, hydrogen and whatever this is, Cl, chlorine, or Br, bromine. What I've just described are either hydrochloric acid or hydrobromic acid as a side product in this case. Side products come into play when we're dealing with substitution type reactions. When we're looking at other type reactions, which we'll get into in the next unit, we won't have side products because it will be a different type of reaction. So we ultimately do have because we have this substitution, one for another, we have a functional group interconversion. That functional group interconversion is an alkane being converted into a halide functional group. Alkane functional group into a halide functional group with our side product. Now, this was just a very general reaction. So let's take a look at how these might be typically set up, how you might be introduced or to this type of reaction if this were a quiz or a test or an exam problem, and how we would ultimately go about solving it. So what we're seeing here is the classic way that I like to put forth these types of organic reactions. It is called a game I like to play named What's in the Box? What's in the box? You're going to be seeing a lot of what's in the box throughout the organic portion of this course, and we have to pick this apart. Well, looky over here on the product profile. That's a box. So we're going to have to figure out what goes in that box, and we have to start being sleuths here. We have to start thinking, okay, what is my starting material? Oh, let's see, what is that? That would be, it's all carbon-carbon single bonds, so that must be an alkane. All right, what is my reagent? Oh, chlorine. Halogenation maybe of something? Halogenation of an alkane. Oh, and here's the kicker. We have light over the arrow. We're going to find, in this case, as we go through our reaction repertoire, that the only time we ever have light over an arrow is in the halogenation of an alkane. So what do? Well, what are we going to put in the box? And I've color-coded this. You might not see color codes in the future, but a halogenation of an alkane is a substitution reaction, meaning on our reagent, one of our chlorines goes over here, and it swaps out a hydrogen, which will go back on it to form our product profile over on the right-hand side. So let's, I want to enunciate one of these hydrogens, or rather carbons right here, because in line drawing we can miss some of that. So let's look at this carbon right here. And if we look at that carbon right there, we can draw it a little bit differently. If you look above, there is actually a carbon right there. Remember in line drawing, at the bends, and the ends, but there's no ends in this, at the bends, we have a carbon, and there are assumed the requisite number of hydrogens on that carbon to satisfy the rule of 4. So that's really what we're looking at. And indeed, I could have highlighted any of these hydrogens, as we'll see momentarily, on this starting material, on this cyclopentane starting material, but I chose that one. Notice, very important to see that if I chose, say, this carbon as my choice right here, and I had two bonds emanating from it and two hydrogens at the ends of these bonds, notice that these two compounds are the exact same compound, just drawn a little bit differently. Very important to notice that as we move ahead. So they're renditions of the same sort of thing, but I chose to use that carbon there. So what happens now when I swap out one chlorine for one of those hydrogens, and that hydrogen comes back here? Well, let's take a look at what happens. We form that chlorine goes over on our on the carbon on my cycloalkane, and that hydrogen, as we saw before, goes onto our side product, hydrochloric acid. That hydrogen right there used to be the one that was on that alkane, that cycloalkane, but it now resides on HCl. So that is indeed what we'd be putting in the box, this structure right here. Now I've enunciated that carbon to now have the chlorine on it and the hydrogen attached to it, but it might be easier for you to just sort of move back into line drawing and draw what we see right here, this alkane with the hydrogen on it. Indeed, drawing it this way, where there is still a hydrogen here, it's just not drawn. It is assumed to be there, but we don't put it in there in line drawing. Now, importantly, as we've said before, that we chose one of those carbons. I'll designate it as carbon A right here. Carbon A. It's important to recognize that all of the carbons on this structure are equivalent. They are indistinguishable from one another. In fact, they're all carbon A, because I could just rotate that cycle a few degrees, and one carbon A would become indistinguishable from the next carbon, indistinguishable from the next carbon, and so on. So that it is important to recognize that there is only one type of carbon on that molecule. Only one type. One type of carbon on the molecule will give one product. Only one type of product. So notice, if I put a chloro group on any of these identical carbons, recognize that every single one of these compounds are different renditions of the same compound. Very important to recognize that as we move ahead and we start thinking about, well, how many possible products, halogenation products, could come from each different alkane. And we will we'll look at that, an example of that, on the next slide. All right, let's look at another one. Again, we have an alkane over on the left. We know that because it's all carbon-carbon single bonds written in line drawing. We have a halogen reagent, and now over the arrow we have heat. So put all of these together as we practice this and have practice in these, we would find that we're dealing with, again, the halogenation of an alkane. And also, I would point out that we have a side product here, which is further evidence of our halogenation of an alkane, but we are indeed playing what's in the box. So we are going to be putting one halogen on that product. So remember what we said before. The number of non-equivalent carbons on the starting material is the number of products we're going to have. So let's look at this carefully. Let's look at, over on the left-hand side, let's look at this carbon right here on an end. I would submit to you that if I rotated this molecule by 60 degrees, that carbon on top would be indistinguishable from this carbon right here, which, if rotated 60 degrees, would be indistinguishable from this carbon right here. So we have 3 carbons right here that are equivalent. They are equivalent carbons. Fair enough. But that's different than another carbon in there. If we look at the carbon connecting them all, that is a very different environment. So that we have 2 types of carbons on this starting material. Indeed, we have the carbon in the middle there that connects all the peripheral carbons. That's definitely structurally different than the carbons that we see on the ends, and those are equivalent. Remember, I could just rotate it 60 degrees, and each of those 2 carbons becomes the next one, and the next one, and so on. They are indistinguishable. Suffice to say now, we have 2 different non-equivalent carbons on that starting material. This means there's going to be 2 products. And to start this, we draw our products such that we draw the single bonded carbon architecture of the starting material in both cases, and then tack on our halogens in this case. Notice, here is my single bonded hydrocarbon product in each case, sort of like a Mercedes sign, and I hung a bromine in this case. Why bromine? Because that is the halogen we're using off of the 1 carbon now, which I see that right here. It has to be covalent bond to bromine. And off of any one of the 2 carbons, covalent bond bromine. Now notice I hung that bromine off of the top carbon. I could have done it on any one of these other ones, and I'd be looking at a rendition of the exact same product. So I have a choice there. But what we have here are 2 different products. 2 different products because we have 2 types of non-equivalent carbons in there. That's how we know we're going to put 2 products in our box, and they're going to be different because they're structurally different. They are constitutional isomers of one another, but they are indeed different products. So let's look at another way of putting together this type of problem. We showed the what's in the box way of depicting an organic reaction. But here's another way of saying, of trying to express this. Not necessarily the same, but it makes you go through the same motions. How many monobromo products would be formed from the following alkane in the presence of Br2 and light? Let's think for a minute. Monobromo product. That means there's 1 bromo. And this is actually expanded to all of the halogenation of alkanes. It's always, we could possibly really hammer it with halogen and light and heat and cause more than 1 halogen to appear on these alkanes, but we're not going to do that. For our purposes, it's always only 1 halogen. A monohalogenated product. In this case, it'd be a monobromo product. Why? Well, because we're using Br2, molecular bromine. It would be if we were using Cl2, molecular chlorine, the question would be for monochloro products, meaning it's only 1 bromine or 1 chlorine on there. So, back to the original question. How many monobromo products would be formed from the following alkane in the presence of molecular bromine and light? So I've drawn it there in line drawing. So it is right here. That is a way of drawing butane in 4 carbons on the ends and the bends, right? So let's look at this. How many different non-equivalent carbon atoms are on here? Well, let's start on this side. Here is an end carbon. Right there. I would hope that you would recognize that if I took that molecule and simply turned it over, that end carbon would then appear on the other end. So those are equivalent carbons. Again, let's look at one of our internal carbons right here at this bend. That's different than an end carbon. I've put that in a different color. It's different because it's an internal carbon. Again, I would hope you would recognize that if I flipped this molecule over, that green dotted carbon would be indistinguishable from this carbon. So thus, we have two different non-equivalent carbons on this molecule. Thus, if we treat that with molecular bromine in the presence of light, we're going to get two products. So this is just another way of explaining, putting A's and B's rather than different colors and dots, the two different types of non-equivalent carbons, so they're two different products of the reaction. So all I'm going to have to do is draw this squiggle right here twice and put a bromo off of one of the A carbons on one and one of the B carbons on the other. And indeed, that's one way to do it. Right here, notice in the case over here, this bromo, if I had put this bromo on this end instead, it would be exactly the same. I don't have to do that because it's the same exactly as I've written there. Over on the other product that I'm showing here, I could draw the bromo instead of on that internal carbon that's shown, I could draw it on the other internal carbon, and indeed it would be another rendition of the same product. So we have options today in organic chemistry. But back to our point, because that original starting material had two different types of non-equivalent carbons, is going to form two different monobromo products, and you can draw them. Let's look at one now that we're looking at a little bit more of an asymmetric molecule, a little more asymmetric. So we have another question in this case. How many monobromo products would be formed from the following alkane in the presence of Br2 and light? Well, let's see how many different carbons we have. I'm going to start with this one right in the center. This is a branch carbon. A branch. There's only one branched carbon in this whole molecule because we can compare this against another internal carbon right here that's different. That is not a branch carbon. The red one has 1, 2, 3 bonds emanating from it. The green one has 1, 2 bonds emanating from it. Slight difference, but different nonetheless. All right, let's keep going. Let's look at some of these end carbons. Let's look at this end carbon right here. That's going to be different because we haven't started describing end carbons yet, just internal carbons, whether they be branched or non-branched. That's an end carbon in blue. But I'm going to submit to you and ask you, what would happen if I took that molecule and just flipped it over? That carbon in blue down there would reflect this carbon in blue up here, because they're described identically. You could describe either one of those blue carbons as an end carbon directly connected to the branch carbon in red. Either one. Now let's look at that last carbon. And it's tempting to say, well, it's an end carbon too, so it must be blue as well. It's not. It's actually different unto itself, because it's described differently. Any description will suffice. So I could say that the blue carbons, we have a blue carbon, and they are connected directly to a branch carbon. Okay, I can't say that with the purple carbon. That purple carbon is directly connected to an internal carbon, but it's not a branch carbon. Very slight difference, but difference nonetheless. So this more asymmetric molecule, we had a number of different carbons associated with it. I see 4 colors there. That means there's 4 different non-equivalent carbons in that structure. So thus, there are 4 different carbons in there, and I'm drawing them down here on the bottom as A, B, C, and 2 Ds. There's 4 different types of non-equivalent carbons. What does that mean? How many monobromo products? Well, 4 different products of reaction. 4 of them, since there's 4 different carbons. Now, all you would have to do is draw this structure 4 times in the box given, and you would hang a single bromine, remember we got to add the covalent bond and then Br, off of one of each of these different carbons to give the product profile we see here. Here we have the bromo coming off of that A carbon. Here we have the bromo coming off the B carbon. Here we have the bromo coming off the C carbon. And here we have the bromo coming off one of those D carbons. So that each of these, while they're all constitutional isomers, they have different connectivity. They are very different compounds. So we have to draw them as such. I'll go back to this that I've said over and over again. This takes practice. A lot of these 4 products that I've drawn here may look, well, they look exactly the same to me. It's okay to say that, but you have to work at this and study these and recognize that they are indeed different, and how to get to them is to recognize the number of different carbons on that original alkane structure. There are a lot of very good practice problems in the unit problems for predicting this, for doing some what's in the box examples, and I'd strongly suggest taking a look at them in order to practice and ply your trade.